For a 400 amp residential service, 3/0 copper conductors will be adequate for the supply conductors. Additionally, 2/0 copper conductors will be adequate for the two 200 amp panels. When dealing with the grounding electrode conductor to the water main, it is highly recommended that you use a single 3/0 THWN-2 copper wire. Be aware that a number 2 copper wire is not likely to fit through the 2.5-inch rigid conduit. For the grounding electrode conductor to the ground rod, a number 6 copper wire is adequate and also adequate to bond the panels. Refer to NEC section 250.50 for grounding electrode conductors. Refer to NEC section 250.94 for bonding requirements. The selection of the correct conductor size is crucial for ensuring electrical safety and compliance with the National Electrical Code, also known as NEC. Firstly, let's discuss the service entrance conductors for your 400 amp service. The question mentioned using two 3/0 parallel cables per phase in a 2.5-inch rigid galvanized conduit for the mass entering the meter pan. To determine if this is acceptable, you need to consult NEC Table 310.16, which provides ampacity ratings for conductors based on their insulation type and temperature rating. Assuming you are using THWN-2 copper conductors, which is a common choice, 3/0 copper conductors are typically rated for 200 amps at 75 degrees Celsius. Since you are paralleling two 3/0 conductors per phase, this would give you a total ampacity of 400 amps per phase, which is adequate for your 400 amp service. However, you must also consider the allowable ampacity adjustment factors as outlined in NEC section 310.15 if there are more than 3 current carrying conductors in the conduit. In your case, you have 6 current carrying conductors in the 2.5-inch rigid conduit, 2 for each phase. Therefore, you need to apply the appropriate ampacity adjustment factor from NEC Table 310.15b3 to ensure the conductors can safely carry the load. If the adjustment factor reduces the ampacity below 400 amps, you would need to increase the conductor size or use conductors with a higher temperature rating. It is also important to verify that the 2.5-inch rigid galvanized conduit is large enough to accommodate the 6 3/0 conductors and their insulation. Refer to NEC Chapter 9, Table 4 and Table 5 for conduit fill calculations to ensure compliance. Next, let's consider the subpanels. The question mentioned using two 2-inch Schedule 80 conduits with 2/0 service entrance cable, also known as SE cable, one for a 200 amp house panel and one for a 200 amp breaker disconnect for a garage panel. Again, refer to NEC Table 310.16 to determine the ampacity of the 2/0 conductors. Assuming you are using copper conductors with THWN-2 insulation, 2/0 conductors are typically rated for 175 amps at 75 degrees Celsius. Since each subpanel is rated for 200 amps, using 2/0 conductors would not be sufficient. You would need to use a larger conductor size, such as 3/0, which is typically rated for 200 amps. Alternatively, you could use conductors with a higher temperature rating to achieve the required ampacity. It is also important to consider the voltage drop in the conductors feeding the subpanels. Excessive voltage drop can cause equipment to malfunction and reduce the overall efficiency of the electrical system. NEC section 215.2b provides guidelines for voltage drop in feeder conductors. To minimize voltage drop, you may need to increase the conductor size or use shorter conductor runs. Now let's discuss the grounding electrode conductor, also known as GEC. The question mentioned using a number 2 GEC to the water main and a number 4 from the panel and disconnect to bond the panels to number 2, and a number 6 ground wire to the ground rod. According to NEC section 250.66, the size of the GEC to the water pipe is based on the size of the service entrance conductors. For a 400 amp service with 3/0 service entrance conductors, the minimum size GEC to the water pipe is number 2 copper. However, the recommendation to use a single 3/0 THWN-2 copper wire for the GEC to the water main is based on the fact that number 2 is the minimum size required. Using a larger conductor, such as 3/0, will provide a lower impedance path to ground, which can improve the effectiveness of the grounding system. It is also important to note that the GEC must be connected to the water pipe within 5 feet of where the water pipe enters the building and must be accessible. The question also mentioned using a number 4 copper wire from the panel and disconnect to bond the panels to number 2. This is not entirely clear, but it appears you are referring to the equipment grounding conductors that connect the subpanels to the main service panel. According to NEC section 250.122, the size of the equipment grounding conductors is based on the size of the overcurrent protective device protecting the circuit. For a 200 amp circuit, the minimum size equipment grounding conductor is number 6 copper. Therefore, using a number 4 copper wire for the equipment grounding conductors would be acceptable, as it exceeds the minimum requirement. Finally, the question mentioned using a number 6 ground wire to the ground rod. According to NEC section 250.66b, the size of the GEC to the ground rod is also based on the size of the service entrance conductors. For a 400 amp service with 3/0 service entrance conductors, the minimum size GEC to the ground rod is number 6 copper. Therefore, using a number 6 copper wire for the GEC to the ground rod is acceptable. In summary, to ensure compliance with the NEC and to provide a safe and reliable electrical system, consider the following. Firstly, verify that the 2/3/0 paralleled cables per phase in the 2.5-inch rigid galvanized conduit are adequate for the 400 amp service. Consider the ampacity adjustment factors in NEC section 310.15 if there are more than 3 current carrying conductors in the conduit. Secondly, ensure that the 2-inch Schedule 80 conduits are large enough to accommodate the 2/0 SE cables feeding the 200 amp subpanels. It is recommended to use 3/0 conductors instead of 2/0 conductors for the subpanels, as 2/0 conductors may not be sufficient for a 200 amp load. Thirdly, use a single 3/0 THWM-2 copper wire for the GEC to the water main, as this will provide a lower impedance path to ground. The minimum size GEC to the water pipe is number 2 copper, but using a larger conductor is recommended. Fourthly, use number 6 copper wire for the GEC to the ground rod, as this is the minimum size required for a 400 amp service with 3/0 service entrance conductors. Fifthly, use number 4 copper wire for the equipment grounding conductors connecting the subpanels to the main service panel, as this exceeds the minimum requirement for a 200 amp circuit. Furthermore, always consult the latest edition of the NEC for the most up-to-date requirement. Electrical codes and standards are subject to change, so it's important to stay informed of the latest revisions. Additionally, it is highly recommended that you consult with a qualified electrician to ensure that your electrical system is installed correctly and safely. Working with electricity can be dangerous, and it's best to leave it to the professionals if you are not comfortable or experienced. Here are some additional points to consider when sizing wires for a 400 amp residential service. Firstly, consider the ambient temperature in the area where the wires will be installed. Higher ambient temperatures can reduce the ampacity of conductors, so you may need to increase the wire size to compensate. Secondly, consider the type of load that will be connected to the service. If the load is continuous, such as lighting or heating, you may need to increase the wire size to account for the increased current draw. Thirdly, consider the distance between the service entrance and the main panel. Longer distances can result in voltage drop, so you may need to increase the wire size to minimize voltage drop. Fourthly, consider the type of conduit that will be used to protect the wires. Different types of conduit have different fill capacities, so you need to ensure that the conduit is large enough to accommodate the wires. Fifthly, consider the local electrical codes and regulations. Some jurisdictions may have more stringent requirements for wire sizing than the NEC, so you need to ensure that you comply with all applicable codes. Some practical implications of wire sizing involve, firstly, safety. Properly sized wires are crucial for preventing overheating and electrical fires. Overloaded wires can generate excessive heat, which can damage insulation and lead to short circuits or fires. Secondly, efficiency. Correctly sized wires minimize voltage drop, ensuring that appliances and equipment receive the proper voltage for optimal performance. Voltage drop can reduce the efficiency of electrical equipment and increase energy consumption. Thirdly, compliance. Adhering to NEC guidelines and local electrical codes ensures that the electrical system meets safety standards and is approved for use. Non-compliant installations can result in fines, delays, and potential safety hazards. Fourthly, reliability. Appropriately sized wires provide a stable and reliable electrical supply, reducing the risk of power outages and equipment malfunctions. Undersized wires can cause voltage fluctuations and intermittent power disruptions. Fifthly, future-proofing. Selecting slightly larger wires than the minimum required can accommodate future electrical needs, such as adding new appliances or expanding the electrical system. This can save time and money in the long run by avoiding the need to upgrade the wiring later. Let's now delve deeper into the specific NEC articles and tables mentioned earlier, starting with NEC section 310.16. This table provides the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air and in raceways. The ampacity values are based on specific conditions, such as the conductor's insulation type, temperature rating, and the number of conductors in a raceway or cable. When using NEC Table 310.16, it's crucial to select the correct column based on the conductor's temperature rating and the termination temperature rating of the equipment to which the conductor will be connected. The termination temperature rating is typically found on the equipment's nameplate or in the manufacturer's instructions. In most cases, the termination temperature rating will be 75 degrees Celsius, which means you should use the 75 degrees Celsius column in NEC Table 310.16 to determine the allowable ampacity of the conductor. However, if the equipment is specifically listed and marked for use with 90 degrees Celsius conductors, you can use the 90 degrees Celsius column. Now, let's move on to NEC section 310.15b3a, which provides the ampacity adjustment factors for more than 3 current-carrying conductors in a raceway or cable. When multiple current-carrying conductors are installed in close proximity, the heat generated by each conductor can raise the overall temperature of the raceway or cable, reducing the ampacity of the conductors. To account for this effect, NEC section 310.15b3 requires that the allowable ampacity of the conductors be adjusted using the factors in NEC table 310.15b3a. The adjustment factors vary depending on the number of current carrying conductors in the raceway or cable. For example, if there are 4 to 6 current carrying conductors, the allowable ampacity must be reduced to 80% of the value in NEC table 310.16. If there are 7 to 9 current carrying conductors, the allowable ampacity must be reduced to 70%. It's important to note that the ampacity adjustment factors in NEC section 310.15b3 only apply to current carrying conductors. Grounding conductors and neutral conductors that only carry the unbalanced current from phase conductors are not considered current carrying conductors for the purposes of this section. Next, let's discuss NEC Chapter 9, Table 4 and Table 5a, which provide the dimensions and fill percentages for various types of conduits and tubing. These tables are used to determine the maximum number of conductors that can be installed in a particular size of conduit or tubing. NEC Chapter 9, Table 4 provides the dimensions of various types of conduits and tubing, including rigid metal conduit, electrical metallic tubing, and flexible metal conduit. The dimensions include the inside diameter of the conduit or tubing, as well as the cross-sectional area. NEC Chapter 9, Table 5 provides the allowable fill percentages for various types of conduits and tubing. The fill percentages vary depending on the number of conductors in the conduit or tubing. For example, if there is only one conductor in the conduit or tubing, the allowable fill percentage is 53%. If there are 2 conductors, the allowable fill percentage is 31%. If there are 3 or more conductors, the allowable fill percentage is 40%. To determine the maximum number of conductors that can be installed in a particular size of conduit or tubing, you must first calculate the cross-sectional area of each conductor, including its insulation. This information can be found in NEC Chapter 9, Table 5. Once you have the cross-sectional area of each conductor, you can multiply that value by the number of conductors to get the total cross-sectional area of all the conductors. Then, you can divide the total cross-sectional area of the conductors by the inside area of the conduit or tubing to determine the percentage of the conduit or tubing that is filled with conductors. If the fill percentage exceeds the allowable fill percentage in NEC Chapter 9, Table 5a, you must either increase the size of the conduit or tubing or reduce the number of conductors. Finally, let's discuss NEC Section 250.50, which covers the grounding electrode system. The grounding electrode system is a network of interconnected grounding electrodes that provides a low impedance path to ground for fault currents. The grounding electrode system typically consists of one or more of the following electrodes: a metal underground water pipe, a concrete encased electrode, a ground ring, or ground rods. According to NEC Section 250.50, all of the grounding electrodes that are present at a building or structure must be bonded together to form a single grounding electrode system. This is typically accomplished by connecting the grounding electrodes to a common grounding busbar in the main service panel. The size of the bonding jumpers that connect the grounding electrodes to the grounding busbar must comply with the requirements of NEC Section 250.66. By understanding and applying the requirements of these NEC sections and tables, you can ensure that your electrical system is properly designed and installed for safety, efficiency, and compliance.